All right, let's get right into it. Today, we're going to talk about a really clever strategy that databases use to handle a constant storm of updates without just grinding to a halt. It really is all about the art of, well, strategic delay.
So to really get the solution, you first have to understand the classic B tree. Think of it as the foundational blueprint for pretty much any database storage engine out there. Its whole design is optimized for one thing: reading and writing big chunks of data, which is exactly how databases have to talk to a physical disk.
But, here's the catch. This super reliable structure has a fundamental problem, a hidden cost that becomes really obvious when you start throwing a ton of changes at it. Just think about your social media feed, right? It's constantly updating. All those little writes expose a major weakness.
So let's break down exactly why every single one of those updates can be so incredibly expensive. You see, the bottleneck, like it is so often, isn't the computer's brain. It's not the CPU. It's the connection to the physical world, to the disk. A traditional update is, a three-step dance. The first two steps? Lighting fast. They happen entirely in the computer's super-fast memory. But that third step, writing the entire modified page back to disk? Oh, that's the killer. That physical write is just orders of magnitude slower. And this leads to this huge issue called write amplification. And here's what's so crazy about it. Even if you only change a single byte of data, just one byte, the database has to rewrite the entire data page. We're talking 4, 8, maybe even 16 kilobytes. It is an absolutely incredible amount of wasted work. So naturally, this brings us to the central question for every database engineer out there. How do we get around this bottleneck, right? How can we possibly make these updates fast without constantly paying that ridiculously heavy price of writing to disk?
And the answer is, honestly, it's surprisingly simple. It's almost philosophical. What if we just waited? And that is the core idea behind what we call lazy B trees. The solution isn't about working harder, it's about working smarter by just delaying the work.
So instead of writing to disk immediately after every little change, we just don't. We hold on to all those modifications in a fast in-memory buffer. We let them pile up, and only when we absolutely have to, we apply them to the disk all at once, in one big, efficient batch.
Okay, so let's see how this brilliant idea actually works in the real world. We're going to take a look at the WiredTiger engine, which you might know from its use in MongoDB.
Now, what's really cool about this architecture is how it's all put together. WiredTiger attaches a little separate update buffer to every single page that's loaded into memory. So updates hit this buffer almost instantly. But, and you can see it in that third point, this creates a new job for reads. Now, when you read data, you have to check both the main page and this little buffer and then merge the results together on the fly.
And this right here perfectly illustrates a classic engineering trade-off. We're making a very conscious choice. We're getting incredible speed for workloads with tons of writes, right? We're slashing that expensive disk I/O. The price we pay is just a little extra complexity and a bit more CPU work whenever we need to read something.
Okay, so that's pretty smart, but what if we could evolve this idea to be even more efficient, especially when updates are happening all over the place in the tree? Well, this leads us to our next example, the lazy adaptive tree, or LA tree.
Layered trees take this a whole step further. Instead of having a little buffer on every single node, they attach buffers to entire subtrees. So picture it like a series of funnels. New updates go into this wide buffer way up high in the tree. Then, every so often, all those updates are efficiently flushed. They cascade down in a big batch into the narrower funnels of the buffers on the lower levels. So what's the key benefit here? Well, this cascading approach creates bigger, much more efficient batches of work. And by grouping more work together, the system spends way less time dealing with locks, which are basically just do not disturb signs on your data pages. This means less contention, which is another huge source of slowdowns in a busy database.
All right, let's zoom out a bit. We've looked at a couple of specific techniques, but what's the fundamental idea here? And why is this so critical for the apps we use today?
This table really lays it all out, doesn't it? A traditional B tree is simple. It's got low read complexity, low memory usage, but man, that write I/O is through the roof. Lazy B trees completely flip the script. We bring that write I/O way down, and we do it by accepting just a bit more complexity on our reads and using a little more memory for those buffers.
And that's really the core takeaway. Laziness, this whole idea of delaying work so you can do it more efficiently in batches, it's a fundamental optimization strategy. It's what makes modern, write-heavy databases fast enough to power the world we live in.
And that leaves us with a really fascinating question to think about.
This powerful principle of doing it later. It's absolutely everywhere once you start looking for it. So where else does this idea of strategic laziness show up